All right, so again, we're talking about electron configuration. So let's take a look at our periodic table, and let's take a look at the power of electron configuration. And the power of electron configuration is that it's very predictive, and it predicts that certain elements are the same and certain elements are different. So if you think back to the beginning of the class, right, we said everything in a row 1 has approximately a charge of +1, and everything in row 2 usually is +2, and so on and so forth. And so in chemistry, the periodic table is organized such that things in the same column are very similar. So elements in the same column are very similar. And this is predicted, or this is predicted experimentally. It's been shown experimentally, and it's also predicted through the power of these quantum numbers, electron configurations, right? And so the question is, why are all of these things in the same column very similar? And the answer is because they have the same number of valence electrons, right? So why are these similar? And the answer is because they have the same number of valence electrons. Valence electrons, an extremely important topic in this course, valence electrons. So obviously you want to know what the heck is a valence electron. So a valence electron is an electron in the highest n orbital. Contrast that to something that's a core electron. A core electron is an electron in the non-highest n orbital. And so these valence electrons that are in the highest n orbital, the valence electrons are always reactive. And so they're the ones that actually do stuff, right? They're the ones that are going to form bonds. They're the ones that are going to be exchanged, so on and so forth. All of these core electrons are very unreactive. And so the vast majority of the time, they're going to do nothing in a chemical transformation. So we're doing chemistry. All we're really messing around is the valence electrons. So these guys do nothing. So let's take a look at some valence electrons and electron configurations and whatnot. Let's start off with lithium. So again, taking a look at lithium. So what I highly recommend is using this pt6.com. pt6.com. It's a very useful resource. So lithium is right over here, if you think about it. So again, 1s1, 1s2, 2s1. So there's the electron configuration for lithium. And if you think about this one, here we have an n equals 1. Here's n equals 2. So the highest n is 2, and you can tell there's 1 electron here. So this has 1 valence electron, and this has, basically these are core electrons. We don't really count core electrons. So 1 valence electron for lithium. And as we said, things in the same column are very similar because they have the same amount of valence electrons. So let's take a look at sodium next. And you can see we'd have to go line by line, left to right. And so this is a lot of stuff to write. And so we chemists can take a little bit of shortcut, right? So technically, this is the way you would write this, right? So far, 1s2, 2s2, 2p6, and then 3s1. And so we can see this, the highest n here is 3, so this has 1 valence electron. And the rest of these are core electrons. And as we said, core electrons generally don't react, so they're not that important. And as you can tell, as we go down the periodic table, we're going to have to write more and more stuff. So what we can do instead is take a shortcut. What we can say is that sodium has the same electron configuration as neon, and then a 3s1 electron. So what we can say here is neon in brackets. That means it has the same electron configuration as neon. and then 3s1. So something important to note is that everything in these brackets that you say, oh, it has the same electron configuration as this is noble gases only. Noble gases only. So you can only use noble gases. And you can tell this represents all of our core electrons, and then we have our one valence electron. So lithium and sodium, very similar elements, always want +1 charge. They only have one valence electron. If we continue down the road, we'll see potassium, right? And so if we think about potassium, it's further, or it's kind of closest noble gas that's has less electrons than it, right? So potassium here, you go one up, it goes to argon. So we can say it has the same electron configuration as argon. Right, so we're at argon, and then we can say 4s1. And so again, here you can tell just one valence electron, one valence electron. And so things in the same column have the same number of valence electrons. So if you draw your kind of little periodic table diagram, one, two, right, everything in group 1 here has one valence electron. Everything in group here has two valence electrons. Everything in group 3 has 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and then 8 valence electrons. So if you look at the periodic table, right, 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, and then 8. For now, we're just going to ignore these transition metals. So we're just focusing on the main block elements. So again, think about aluminum. Aluminum would be right here. And if we check out where aluminum is, it's in period 3. So we can say it has the same electron configuration as neon. Right, so we're at neon, and then we go 3s2, 3p1. So how many valence electrons does this have? Well, you see they're both n equals 3, so they both count as valence electrons. So there's a total of 3 valence electrons there. So be able to tell how many valence electrons an element has based on which column it's in. And remember, for now, ignore the transition metals.